Hello, everyone. Welcome to this new webinar of Biostimulant.com, and thank you for joining us today. I'm Erika, and before to get started, I would like to give you a couple of information. Firstly, this webinar is recorded, and the recording will be available on Biostimulant.com website in the next days. Secondly, we invite you to use the Q&A box that you can find at the bottom of your screen to submit questions. We will collect your questions and answer to at least some of them at the end of the webinar when we will have a Q&A section. The webinar is expected to last 1 hour, more or less. The topic of today is plant biostimulants and mitigation of greenhouse gas emissions in crop production. I would like to introduce our speaker, Sara Rajabi Hamedani, postdoc researcher at Tuscia University in Italy. Welcome, and I leave you the floor.
Thank you. Good afternoon, everyone. It's a pleasure to welcome all of you to this webinar, and I'm going to talk about plant biostimulants and mitigation of greenhouse gas emissions in crop production. My talk will be in 5 parts. In the first part, I will explain sustainability concept, and in the next part about LCA concept. Then I will state history and motivation of LCA. In the fourth part, I will talk about carbon footprint concepts, and finally, I'll go on to talk about biostimulants and case studies. Sustainability is a relatively new concept introduced in 1987 by United Nations World Commission for Environment and Development in response to challenges of climate change, increasing pressure on the environment, and subsequently their social and economic consequences. Sustainability defines as meeting the needs of the present generations without compromising the ability of future generations to meet their own needs. In 2017, 193 member states of the United Nations adopted 17 goals to end poverty, protect the planet, and ensure prosperity for all as part of a new Sustainable Development Agenda by 2030, setting targets for the present generations in order to meet their needs. So, in other words, sustainability is a capacity to endure in a relatively ongoing way across various domains of life. In line with protection of the planet, environmental sustainability is the responsibility to conserve natural resources and protect global ecosystems to support health and well-being now and in the future. Therefore, environmental sustainability aims to responsibly avoid depletion and degradation of natural resources, including material and energy, and also to avoid environmental contaminants like carbon dioxide and particulate matters arising from human activities. In order to achieve sustainability goals, we need to manage measurable issues. In other words, what is not measured is at risk of being neglected. Hence, there is a need for comprehensive and robust tools to help decision makers identify the solutions that support sustainable development. The decisions must have a system perspective, consider the life cycle and all relevant impacts caused by the solution. In this way, life cycle assessment, called LCA, is a powerful tool to measure environmental issues. That's why there is a strong and growing need for professionals who understand or even master this tool and who know how to critically appraise and use the information that it provides. But maybe you are curious enough to know what characteristics of LCA make this tool, make it powerful to measure issues. First, the life cycle metaphor is borrowed from the field of biology. For example, the life cycle of a butterfly starts with an egg, which bursts and make a larva, and then turns into a pupa from which a butterfly emerges, then eventually dies after laying eggs for the cycle to be repeated. In the same way, a man-made object starts its life cycle by harvesting and extraction of resources, followed by production, use, and eventually management of the object as waste, which is the end of the life cycle. Recycling or reuse can be seen as new eggs for the life cycles of other man-made objects. The other characteristics is life cycle covers a broad range of environmental issues, typically around 15 issues. The core reason for considering multiple environmental issues is to avoid burden shifting. Burden shifting happens if efforts for lowering one type of environmental impact unintentionally increase other types of environmental impacts. Another characteristic is LCA is a quantitative approach. So it can compare environmental impacts of different processes and product systems, and then it can judge which products or systems are more environmentally friendly, and then indicate the process that contribute the most to the overall impact, and therefore should receive attention. And last but not least is science-based approach of LCA. The models of the relationship between emissions and impacts are based on proven causalities, like empirically observed relationships. For example, a relationship between the concentration of phosphorus in a lake and the observed numbers of species and their populations. So LCA use this approach, use this relationship, and then measure the impacts. So after talking about characteristics, it is time to know about the history. Initial LCA studies focus on energy. For example, one of the first studies addressed zero-emission vehicles in California, when the state policies were encouraging producers to indicate and to increase the production of these vehicles. These vehicles worked with lead-acid battery, and they didn't need any tailpipe, so no emission were released to the environment. So they were really attractive and appealing compared with gasoline cars. But one study in a science journal substantiated this policy cannot achieve its intended goals. And what are the problems and what made this policy fail? So the problems were related to the batteries, because they regularly needed to be needed recharging, and to recharging they need electricity, and the production of electricity releases emissions into environment. In addition, lead-acid batteries were heavy, and in particular, lead production and its recycling causes a significant amount of emissions to the environment. Therefore, these vehicles damage the environment and were actually not carbon neutral. The initial LCA studies were also carried out to choose material in industrial products. For example, studies were answering which material are appropriate for packaging, paper, plastic, or cotton. In 1969, first multi-criteria study was performed for a Coca-Cola company. They wanted to compare glass with plastic containers. 3 criteria were considered in this study: production, transit, and end of life. Results show that the plastic bottle was the best choice, contrary to the expectations. Indeed, plastics could be internally produced in Coca-Cola company, and there's no need any outsourcing and another company for production. Moreover, they had lower weight, and therefore it brings advantage in transit. And finally, plastics were recyclable versus glass that is disposable. This study was never published, but the questions on validity of this study led scientific community to start defining a standardized process for performing similar studies. Currently, LCA is defined as a practice of organizing parts of the life cycle associated to product, process, or activity. It's a common tool used to assess environmental, social, or economic performance, and it's characterized into various scopes, such as the environmental life cycle assessment, recognized as a life cycle assessment, social life cycle assessment, SLCA, life cycle costing, LCC, and life cycle sustainability assessment, LCSA. And it's not an exact science because of some limitations of this method, such as uncertainty in data collected for whole life cycle or modeling missing impact indicators. So that's why it still needs continuous research to develop. And finally, we can say LCA cannot directly solve all environmental consequences, but it can identify them and be helpful in decision making. All LCA studies categorized by the scope of these studies. And they have 2 main scopes. Some life cycles may focus on the process of making the product up to the point of leaving the factory and have a cradle-to-gate view, where the word of gate refers to the factory gate. Returning to the in this part and returning to the natural life cycle. Life cycle means going from the birth of the product to its death. This kind of view is often called a cradle to grave, where the cradle represents the birthplace of the product, and the grave represents what happens to it when we are done with it, often to be thrown into a landfill. A full understanding of the environmental impacts of products requires an exploration and assessment of everything that goes into the development, use, and disposition of those products. We have different categories of environmental impacts. Environmental impacts arise from emissions to air, called airborne emissions, emissions to water, or waterborne emissions, and soil contaminants. Airborne emissions consist of greenhouse gases from burning fossil fuel, representing as carbon dioxide, methane, and nitrogen oxide, and also particulate matters that are demonstrated into dust and smoke large enough to be visible. These particles are pollutants emitted from power plants. Another group of emissions degrades water quality by leaking compounds like nitrate and phosphorus to the groundwater. These emissions are consequences of improper application of fertilizers and inappropriate management of municipal solid waste. Soil contamination, which degrades land, is also caused by the presence of toxic compounds in soil due to the concentration of pesticide and industrial waste. Among all environmental issues, global warming draws immense attraction. And in order to tackle this issue, policymakers, on the one hand, enacted carbon tax, and on the other hand, encourage and develop carbon offset projects like reforestation for converting fossil-based activities like energy generation and aviation industry into carbon neutral. Therefore, carbon footprint that measures merely gas emissions that cause climate change are more focused than ecological footprints. Carbon footprint follows LCA approach to evaluate the greenhouse gas emissions caused by the manufacture of a product or any given activities that contribute to global warming. But since importance of an approach relies on its functionality towards facing challenges, let's see which questions can be responded by performing LCA and carbon footprint. For example, in case of transportation and car production, which phase of life cycle of a car has the largest impact on the environment? Manufacturing, use phase, or driving, and or fueling car, and what can be suggested to reduce this impact? Or these questions can be also about the human eating habits. For example, to what extent being vegetarian can reduce impacts on the environment, or if shopping from local food fairs can be a wise choice, or large markets, considering the distance, and how significant are these differences. One of the hot topics in food security argument is excessive use of agrochemicals for increasing crop productivity in response to growing population and global food demand. This attitude has eventually led to seriously negative impact on soil quality and also on terrestrial and aquatic ecosystems. Hence, alternatives such as biostimulants can be substituted for chemical fertilizers and guaranteed productivity of crops. Biostimulants are the substances or microorganisms or products able to enhance nutrient use efficiency, mitigate the adverse effects of abiotic stress, and boost edible product quality. In order to comprehend whether and to what extent biostimulant application for growing crops can achieve environmental benefits, 12 case studies are introduced and analyzed for corn, watermelon, zucchini, and spinach. The main audiences of this study are farmers and specialists who are following confident approaches to boost the quality and quantity of their products, and policymakers who promote biostimulants for sustainable development. In order to analyze mycorrhizal fungi role in boosting water use efficiency for watermelon production, one study in Harran University in Turkey defines 4 treatments. These treatments are characterized by use or non-use of mycorrhizal fungi and standard or reduced irrigation. The results of this study have been published, and we extracted data acquisition of carbon footprinting from this study. Second case study focuses on improvement in efficiency of nitrogen consumption for maize cultivation in response to vegetal biostimulant application. Therefore, 3 treatments were defined in the experimental camp in Bulgaria. These treatments are distinguished by use and non-use of vegetal biostimulants and reduced nitrogen fertilizer consumption. We performed carbon footprint analysis by elaborated data from the published results. Third case study investigates the impact of mycorrhization on mineral and organic fertilizer consumption intensity. In zucchini production, in the case of zucchini production. So in the experimental farm of Tuscia University, 4 treatments were defined based on use and non-use of arbuscular mycorrhizal in both terms of mineral and organic fertigation. But the last case study monitors the effect of a vegetal-derived protein hydrolysate biostimulant application on nitrogen fertilizer regime in a spinach crop. And the farm activities were performed in a University of Naples, and the treatment involved various combinations of nitrogen fertilizer regimes. Foliarly treated or untreated with a vegetal-derived protein hydrolysate biostimulant. The framework of LCA has been determined in 2006 in compliance with ISO standards. This framework consists of 4 main steps, which all LCA studies are required to follow these principles. First step is a definition of goal and scope. In this step, objective of LCA study must be clarified. Objectives can be determined by responding to some questions. For example, how extensive is the scope of our study? The kind of LCA, either cradle to gate or cradle to grave, is determined by this question. And also processes and sub-processes are also defined in this phase. Another question is, what is the functional application of end product of the system? For example, a power plant is a product system that has a function of generating electricity. So 1 megawatt electricity production can be a proper functional unit for this system. But for another system, we have different functionality for different systems. The other questions that we should answer here is, what is the intended application of LCA in our study? Is it a comparative study, 2 products with the same application are compared, or is it an assessment of technological changes on environmental profile of a product? So that's why the goal of this study is to assess the overall environmental impact of crop production chain. That here, environmental impact is global warming potential. And this study is a comparative study to identify optimum farming management for different crops. This study is carried out in a cradle to gate scope, including all phases from raw material production, cultivation to harvest of crop produce. And because we are dealing with the agricultural production system, the functional unit will be 1 ton of crop produce. After defining goal and scope, the next step is preparing a list of data required for each sub-process. This step of life cycle assessment study is very time-consuming because it needs a deep and good research to collect all data related to processes. If we face lack of data for each sub-processes, we can modify system boundary by removing that sub-process and redefine the scope of the study. Here, in system boundary, we have all processes related to watermelon and maize production. Inputs of these processes include fertilizer, electricity for irrigation, and whatever needed to cultivate these crops. Outputs are divided into 2 parts. One is emissions arising from each process to air and water. For example, application of fertilizer can cause eutrophication, which has an impact on water quality degradation. But in carbon footprinting, we just take into account greenhouse gas emissions, including carbon dioxide, methane, and the nitrogen oxides. The other part of output is products, watermelon and maize crops. Here we can see the table of all inventory data in detail. For maize, all processes related to zucchini and spinach production, and also greenhouse gas emissions are included in the model. And here we have zucchini and spinach data in detail. The next step based on an LCA framework is the impact assessment. In this phase, impact assessment methods convert all material and energy of the system to conversational indicators. Different impact assessments exist, and they are distinguished based on presenting environmental results. For carbon footprint analysis, Intergovernmental Panel on Climate Change, that stands for IPCC, is a method specifically developed for analyzing climate change impact. Impact assessment methods report impacts into the units as a reference to a substance. In IPCC method, results are presented in carbon dioxide equivalents. Various softwares are available to develop LCA model, including general softwares such as CIMAPRO, Gabi, or OpenLCA, and also specialized software. But here we developed LCA model in CIMAPRO software as it's more professional than the other one. And about the result. Thanks to biostimulants, watermelon productivity is improved. The treatment with standard irrigation and biostimulant application has the highest yield among other treatments. And then water use efficiency also increases in touch with biostimulants. This increase can be by 26% in treatment with standard irrigation and 46% in treatment with reduced irrigation. The comparative environmental results of these 4 treatments also verify beneficial actions of biostimulant on global warming mitigation. Overall, comparing the treatments with biostimulant application, the one with standard irrigation has the lower carbon footprint. On the other hand, mycorrhizal treatment with reduced irrigation can save higher carbon release than mycorrhizal treatment with the standard irrigation rate. In second case study, the similar results are obtained. In fact, biostimulant application can rise maize production while use the lower rate of fertilizer. So it can lead to increasing nitrogen fertilizer efficiency by 56% in maize cultivation compared with other treatments. Comparing environmental results of 3 treatments also indicates that application of biostimulant can decrease global warming potential and produces a more environmentally friendly crop. Indeed, increasing crop yield in one hand and decreasing nitrogen fertilizer application in another hand lead to 12% carbon saving in treatment with biostimulant application. In zucchini case study, the highest fruit yield belongs to mycorrhizal plants subjected to standard mineral fertilization, while non-mycorrhizal plants with organic fertilization provided the lower value. Also, the result shows that mycorrhization increases nitrogen use efficiency of zucchini production in both mineral and organic fertilization treatments. But the impact of mycorrhization in case of organic fertigation is more tangible. It's 12%. Since the functional unit selected is 1 ton of harvested crop, an increase or decrease in fruit yield has a reverse impact on total carbon dioxide emissions. The result shows that the mycorrhization reduced the total emissions of carbon dioxide equivalent per ton of marketable zucchini in both mineral and organic fertigation treatments. The lowest value of carbon dioxide equivalent emissions or carbon footprint belongs to the mycorrhiza treatment with mineral fertilization. The mycorrhization reduced the emissions of all inputs used per 1 ton of zucchini due to an effect that increased the production of marketable zucchini or zucchini productivity, that increased zucchini productivity with the same input consumption. In fact, mycorrhization improved the efficiency of resource use, for example, fertilizer, which has a direct connection with controlling carbon emission. In case of process contribution, diesel that's mainly used for greenhouse heating was the main contributor to the total carbon footprint. In a spinach case study, the production of spinach was increased by increasing the nitrogen fertilization rates, while biostimulant application enhanced spinach yield, especially under lower nitrogen supply. So the highest spinach yield was obtained in treatment with higher nitrogen fertilizer and biostimulant application, but the lowest one belongs to the treatment with neither biostimulant application nor a nitrogen fertilizer use. The nitrogen use efficiency also was higher in the treatment with biostimulant application compared to those with only mineral fertigation. The key results of comparative carbon footprint results shows that the foliar applications of biostimulant lead to a reduction of the total carbon emissions per ton of spinach production compared to the treatments with the same amount of fertilizer but without foliar application of biostimulants. The highest carbon emission reduction, 24%, belongs to the unfertilized treatment with application of biostimulants, whereas the reduction was limited to only 7% with the application of biostimulant in highest rate of nitrogen. And finally, as a global result, biostimulant application proved to be an effective way to reach sustainability objectives. First, biostimulant application is able to heighten productivity of crops. Since productivity crops concept is in the inverse of resource intensity, increasing productivity can diminish and can decrease input consumption, which is in line with sustainability goals. And second, the application of biostimulants mitigates climate change and therefore enhances ecological quality of crops. And this character can bring more commercial opportunity to those crops because it's an indication of the quality improvement of a product. Indeed, the greener products can earn more revenue in the market. So that's why my presentation today. And for getting more information about this result and about these studies, you can see the result of these case studies in one published book, and also in one open access article that is published in Sustainability Journal. Thank you for your time and attention, and I'm open for your questions.
Okay, thank you for your very interesting presentation and for sharing how biostimulants can mitigate climate change and also increasing the marketable value of products. As you anticipated, now we will have a Q&A section. So I remember to all of you that you can submit questions through the Q&A box that you can find at the bottom of your screen. We have already received some questions, so I'll start immediately with the first one. The application of biostimulants can entail a substantial reduction in greenhouse gas emissions. Do you have information on how the different conditions like weather or soil type can affect this activity? And can also the specific combination of biostimulant and crop variety modify the result?
So I would answer this question by pointing out concept of climate change indicator. As global warming potential is measured per ton of crop produce as a functional unit, one increase and or decrease in crop productivity can affect the climate change indicator. For example, the germination and early development of many crops are sensitive to temperature factor, and the presence of biostimulants stimulates the resistance of plants to water and temperature stresses and heavy metals. So in the same way, crop productivity can be influenced by a specific combination of biostimulant and crop, and consequently modify global warming potential.
Okay, thank you. And I go ahead with the next question. The timing of application of biostimulants, especially for foliar biostimulants, is relevant. And can you explain which is the timing of application used in the showed trials?
About the timing, so the biostimulant effectiveness to tackle the stressful condition depends on several factors, like timing, timing of application. The application of a biostimulant can be done with different timings: before the stress, during the stress, or even after. Proper timing of application, biostimulant application, is during crop development. And it differs from species to species. It also depends on the most critical phases for crop productivities. So identification of the right time of biostimulant application is as important as determination of exact dose, and it should be considered. to avoid high cost and also unexpected results, and to avoid waste of product. Yeah.
Okay, thank you. So we have just received another question. And first of all, thanks for the nice presentation. And how can be valorized at commercial level a product obtained with biostimulants having low carbon footprinting?
Okay. Can I ask you to repeat the questions?
Oh, yes, yes, of course. No, of course, don't worry. So the question is, how can be valorized at commercial level a product obtained with biostimulants having low carbon footprinting?
Okay, it depends on the policymakers, okay, and it should value added to the price of the products, and like the products that now are purchasing in the organic shops, that has a higher value than the other ones, and that's why one label that's added to the one package of the product that is used, for example, the biostimulant, it has a higher revenue for that product.
Okay, so one more question, that is the last, and is we have seen that in your presentation, application of vegetal biostimulants and microbial biostimulants containing mycorrhiza mitigate greenhouse gas emissions in crop production. Can we expect the same activity from other types of biostimulants, for example, seaweed or animal protein hydrolysates?
Yeah, of course. The seaweed and animal protein hydrolysates are also active biostimulants with the same activities, but the result may be contrasted, maybe they are different because of the different origin of biostimulants, animal or vegetal origin, and also because of the different production process. Is it a chemical production process or enzymatic hydrolysis? Or even it depends on the plant species or the rates of biostimulant application in the for cultivation phase. Yeah, it depends on this, but actually they have a same role.
Okay, thank you. It was the last question, and thank you again also for your insightful presentation of today. I would like to thank everybody for attending today, and I would like to remind you that if you still have questions, you can submit them on biostimulant.com website, and our scientific committee will get back to you with the answers. Besides, I would like to remind you that the recorded version of this webinar will be available on biostimulant.com website and on our social media in the next days. So check it out. Have a nice day, everybody, and see you on the next webinar. Bye.